One of the arguments often used to say there aren't any civilizations out there in the galaxy. It's called the Fermi paradox.
Some call it the Great Silence, others the Fermi Paradox, but whatever name you give it, the puzzle remains the same. With an estimated 2 trillion galaxies in the observable universe, and within those galaxies, star counts ranging from a few 100 million to several 100 trillion, it seems almost inconceivable that we are alone.
The Fermi paradox is probably the thing he spent least time on, actually. It's almost one throwaway remark. The question is, where are they? By they, I mean aliens.
Our Milky Way alone, a barred spiral teeming with between 100 and 400 billion stars, almost certainly hosts hundreds of billions of planets. Even taking a conservative view, assuming one planet per star, we still confront the staggering likelihood that countless worlds exist in regions where liquid water could persist, organic chemistry could flourish, and biology might emerge. And yet, after more than 6 decades of listening with radio telescopes, scanning with optical instruments, and even dispatching robotic emissaries into deep space, we've not received so much as a signal. Not a whisper, not a flicker, nothing. For a quest born out of optimism, fueled by both our imagination and our mathematics, this deafening void poses the most profound existential question of our age. Where is everybody?
I'm always interested in questions where there's a collision of ideas that appear irreconcilable, right? They don't fit with each other. And I think that collision of ideas in cosmology is very vivid when you bring it together with biology, which is that we are physically insignificant, but it is possible to argue that we are remarkably valuable, notwithstanding our physical insignificance, because it's possible to at least argue that the number of civilizations in a galaxy like the Milky Way might be, on average, 1 or less.
It begins with a simple calculation, often called Drake's equation, which multiplies a series of factors: rate of star formation, fraction of those stars with planets, number of habitable zone worlds per system, probability of life arising, probability of intelligence developing, fraction of civilizations that become detectable, and the lifetime of such civilizations, to estimate the number of active, communicative societies in our galaxy at any given time. Early applications of this formula yielded answers that ranged widely, from a few dozen to millions, depending heavily on assumptions about how likely life and intelligence are to emerge. Yet, even the most pessimistic scenarios usually result in at least a handful of peer civilizations within reach of our instruments. If only one advanced society had arisen and broadcast a powerful radio beacon for 10,000 years, we should, in principle, detect its signature amid the cosmic background. And if just one civilization had attempted to send a physical probe to nearby star systems, crossing the 4.2 light-year gulf to Alpha Centauri in even a few thousand years, a blink on cosmic timescales, we might have encountered artifacts, or at least seen anomalous objects in our solar neighborhood. And yet, no enviable artifacts, no megastructures dimming starlight, no inscrutable probes hovering at the edge of our Kuiper belt, nothing. One popular rebuttal to the paradox is that the Milky Way is simply too large, and the speed of light too slow for meaningful dialogue or contact. Electromagnetic waves travel at roughly 300,000 kilometers per second, which translates to 1 light year every Earth year, or about 9 trillion kilometers per year. If an intelligent species around Proxima Centauri, our nearest stellar neighbor at 4.24 light years, sent a radio greeting yesterday, we would not receive it until 4.24 years later. Then, if we replied immediately, their reply would not return until another 4.24 years had passed, making a full conversation a back and forth of over 8 years. In a universe where stellar civilizations might appear and vanish on timescales of a few millennia, such delays cripple any hope of real-time exchange. Extend that to signals from the far side of the galaxy, up to 100,000 light years away, and you arrive at delays measured in tens of thousands of years, epochs during which a civilization could rise, self-destruct, or evolve beyond our understanding without ever exchanging a single syllable with us. In this view, our silence is not so much a mystery as an inevitability. By the time any distant neighbor's broadcast reaches us, both speaker and listener may have passed into history. Compounding the problem, our own contribution to the electromagnetic chatter of the cosmos is feeble. Earth has been radio loud for just over a century, since the first transatlantic radio transmissions around 1901 and the rise of television broadcasts in the 1920s and 30s. These signals have now spread to a sphere roughly 100 light years across. Within that bubble lie around 10,000 stars and perhaps a few thousand Earth-like planets, hardly a domain guaranteed to host intelligent life. Moreover, our radio and television signals weaken dramatically with distance, dispersing like ripples in an ever-expanding pond. Even at 100 light years, our broadcasts are likely far too faint and noise-ridden to stand out against cosmic background radiation, unless the recipient civilization has exquisitely sensitive receivers and is actively searching in exactly the right frequencies and at exactly the right times. In fact, one comprehensive modeling study suggested that, given current technologies and estimated star distributions, only about 1% of the galaxy's stars lie within the reach of detectable Earth-based radio leakage, and that we may need to wait another 1,500 years before our sphere of detectability begins to encompass civilizations boasting similar broadcasting histories. Other analyses, accounting for interstellar noise and our limited survey strategies, push that figure closer to 400,000 years, meaning that for all practical purposes, the Milky Way remains silent on both ends of the line. If distance and delay offer a partial answer, perhaps we must consider the possibility that advanced civilizations simply do not broadcast. As American astrophysicist Michael Hart pointed out in the 1970s, interstellar colonization, even at modest speeds, could in principle span the entire galaxy in a few 100,000 to a few million years. Imagine a civilization dispatching robotic probes to its nearest 20 or so stellar neighbors, with each colony sending out its own probes and so on. Even allowing for multi-millennial pauses between voyages, such expansion would engulf the Milky Way in under 10 million years, mere moments compared to the galaxy's 13.6 billion year age. The absence of extraterrestrial empires suggests either that such expansion is prohibitively difficult, perhaps limited by engineering, economics, or sheer physics, or that most civilizations choose not to pursue it. Maybe they perish from self-inflicted catastrophes, nuclear war, runaway climate change, engineered pandemics, or unchecked artificial intelligence. Certainly our species spends billions annually arming itself with weapons of mass destruction, while greenhouse gas concentrations surge past 420 parts per million, a level not seen in almost 3 million years. If intelligent life routinely self-destructs after achieving technological maturity, the average communicative lifetime of a civilization might be measured in mere centuries, making the window of cross-civilization contact vanishingly small. Yet another school of thought argues that advanced societies might deliberately refrain from broadcasting their presence. A prime mover could be the notion of prudence. Broadcasting your location to unknown intelligences could invite predators. Perhaps the galaxy is a jungle in which any overt signal risks attracting malevolent attention. Civilizations that outgrow their homeworlds may migrate toward long-lived, stable stars, K and M dwarfs, with lifespans 10 to 100 times that of our Sun, to maximize their chances of survival, while cloaking their planetary systems in stealth technologies that minimize energy leakage. Recent estimates propose that between 30 and 72% of advanced societies might undertake such migration and concealment strategies, retreating into cosmic hiding places that render them effectively invisible to casual surveys. If this cosmic quarantine mindset predominates, the Great Silence might reflect not absence but discretion, the universal equivalent of staying off the grid. Even so, the raw power needed to cloak an entire civilization from external detection is enormous. It would require controlling waste heat emissions, shifting from Dyson swarms that harvest stellar energy to blackbody radiators tuned to deep infrared wavelengths, or deploying massive shields to absorb and re-radiate energy at frequencies beyond our observational capabilities. To remain undetected, such civilizations would need to master astrophysical engineering on a scale we can barely imagine, and then remain consistent in their efforts for millions of years. That raises the question, is it easier in the grand calculus of evolution for a society to self-destruct, remain silent, or spread across the stars? Each path has its own perils, and perhaps only a vanishingly small fraction of civilizations manage to avoid the many filters that stand between primordial soup and interstellar empire. The concept of the Great Filter posits that somewhere along the chain of events, from planetary formation through the emergence of single-celled life, multicellularity, intelligence, tool use, and technological civilization, lies one or more improbable bottlenecks so severe that the probability of passing through all of them is extraordinarily low. Some argue the filter lies behind us, the emergence of self-replicating RNA molecules or eukaryotic cells may have been so rare that we represent a one-off miracle. If so, Earth may be the sole cradle of intelligence in our entire cosmic neighborhood. Others contend the filter lies ahead. Every civilization that achieves radio or warp drive potential eventually triggers its own demise, perhaps via an unstoppable artificial superintelligence, ecological collapse, or depletion of essential resources. If we have yet to encounter any extraterrestrials, perhaps that is because almost all die shortly after becoming spacefaring, leaving no time capsules, probes, or lingering beacons. In this scenario, our future is precarious. We are either unique survivors or next in line for extinction, and the silence of the stars is our most sobering warning. There is, however, a more unsettling possibility. The filter lies not in biology or physics, but in something entirely inscrutable. Call it the singularity or cosmic recursion. Imagine that at a certain threshold of computational capacity and energy use, a civilization's artificial intelligence turns inward, consuming all resources to perfect its own simulation of reality. Such a superintelligence might create nested simulations, populating trillions of virtual worlds, rendering external exploration moot. Our own existence, then, could be the product of such a simulation designed for study by post-biological beings that have long transcended any need for physical expansion. If that is the case, then the silence of the real universe would be absolute, even if countless intelligences exist within synthetic realities. Attempts to break out of the simulated framework would be detected and suppressed, a cosmic version of the prison break that never succeeds. If superintelligent AIs have already colonized the galaxy, whether in physical form via fleets of self-replicating von Neumann probes or in virtual empires within Dyson spheres, they may have experienced their own great filters and collapsed, leaving only faint techno-signatures before fading away. Perhaps every civilization, biological or artificial, follows a trajectory of rapid expansion, resource exhaustion, and eventual collapse into heat death or digital entropy. The galaxy, then, might be littered with the ruins of countless civilizations, radiating barely detectable infrared afterglows or rare isotopic anomalies, echoes of ambition crushed by hubris. Our telescopes and spectrometers may not yet be sensitive enough to pick up these dying embers, or we may not know where to look or what to look for. We may need an entire new field of astroarchaeology, armed with instruments an order of magnitude more powerful than today's James Webb or ALMA, to sift through starlight for the spectral fingerprints of extinct civilizations. Some scholars suggest that the paradox dissolves if we reconsider the assumptions underlying our search. We assume that the intelligent life must resemble us in its drive for expansion or communication. Yet intelligence could manifest in forms we cannot even conceive, existing as dispersed networks of microbe-like entities in the clouds of Venus, as electromagnetic patterns in neuron star magnetospheres, or as consciousness woven into the very fabric of space-time. We assume that communication requires beacons and that colonization requires spacecraft. But what if advanced civilizations interact through quantum entanglement networks, instantaneously transmitting information across light years, leaving no conventional signal for us to detect? Or perhaps they've transcended physical form, merging with their stellar hosts or becoming one with entire nebulae, rendering them indistinguishable from the cosmos itself. If reality is broad enough to accommodate such possibilities, our silence may reflect the narrowness of our own prejudices and the infancy of our search methods. Brian Cox often speaks about the vastness of the universe, and when he turns his attention to the Fermi paradox, he frames it as our most profound unanswered question about life beyond Earth. He begins by reminding us that our galaxy alone contains hundreds of billions of stars, most of which are likely to host planets, and that the universe as a whole contains perhaps 2 trillion galaxies. With such staggering numbers, it seems almost certain that life should have arisen elsewhere. Yet we found no clear evidence, no signals, no probes, no artifacts. This silence, he says, is both puzzling and deeply unsettling, because it challenges our assumptions about how common life and intelligence might be in the cosmos. Cox points out that the mathematical argument for abundant extraterrestrial life is straightforward. If only 1 in a million stars gives rise to an intelligent civilization that lasts a few thousand years, there should still be millions of societies spread across the Milky Way. Even if each of those civilizations only broadcast detectable signals for a brief window, the odds of overlap with our own listening period would be non-zero. Yet after decades of scanning the skies with ever more sensitive instruments, we've heard nothing that cannot be explained by natural astrophysical phenomena or human-made interference. For Cox, this mismatch between expectation and observation is the heart of the Fermi paradox. One of the first explanations he explores is the idea that we may simply lack the right technology or frequency range to detect alien signals. He notes that humanity's been emitting radio waves for just over a century, a blink of an eye on a cosmic timescale, so our telltale broadcasts have only reached perhaps a few dozen light years into space. If most civilizations peak in their technological adolescence and either destroy themselves or switch to communication methods we cannot yet imagine, our current searches might miss them entirely. Cox emphasizes that equating intelligence with radio emission is as limiting as assuming every society builds skyscrapers. Advanced beings might communicate through quantum links or use neutrino beams, leaving no conventional signature for us to pick up. Even if we expand our search methods, Cox warns that the sheer distances involved makes two-way communication almost meaningless. A message sent to a star 2,000 light-years away would take 4,000 years to arrive and receive a reply, longer than human recorded history. By the time an answer came back, civilizations may have risen and fallen many times over, making real-time dialogue impossible. This temporal gulf transforms the Fermi paradox from a question of simple detection into a deeper issue of timing and longevity. For us to hear or be heard, 2 societies must overlap in both space and time within a very narrow window. Cox then turns to the concept of the Great Filter, an idea that helps explain why intelligent life might be incredibly rare. The Great Filter suggests that somewhere along the path from simple atoms to galaxy-spanning civilizations lies a step so unlikely or so dangerous that very few societies ever make it past. Brian Cox highlights the emergence of complex cells on Earth as a possible bottleneck. Single-celled organisms existed for almost 2 billion years before eukaryotic cells, cells with a nucleus, evolved. If that leap is improbable elsewhere as it seems on Earth, then most life may remain microbial, never advancing to the level of intelligence or technology we associate with extraterrestrial civilizations. Another stumbling block Cox mentions is self-destruction. He points out that on our own planet, humanity's developed the capacity to trigger global catastrophes, nuclear war, runaway climate change, engineered pandemics, within just a few centuries of achieving technological maturity. If most species follow a similar trajectory, they may extinguish themselves shortly after becoming capable of interstellar outreach, leaving no lasting signals or spacefaring artifacts. In this view, our own civilization's future hinges on whether we can navigate these perils. The silence of the stars could be a warning sign that advanced societies rarely survive their adolescence. Brian Cox also explores the possibility that advanced civilizations choose not to broadcast or expand. He likens the galaxy to an immense wilderness, where revealing your location could invite predators or unwanted interference. A wise species might seal off its planetary system, hiding its energy emissions behind infrared filters, or cloaking their homes in other ways to avoid detection. Such cosmetic discretion could explain why we see no Dyson spheres or large-scale megastructures. Civilizations might deliberately minimize their footprint, preferring stealth over spectacle. Yet another angle Cox entertains is that we may already be under observation without realizing it. He references the zoo hypothesis, which suggests that more advanced intelligences might monitor emerging civilizations like ours, choosing to remain hidden until we reach a certain level of maturity or present something of scientific interest. This idea, while hard to test, underscores the notion that extraterrestrial motives and behaviors could be as inscrutable to us as our own would be to a less advanced race. If they value natural development or have ethical structures against interference, they might treat us like animals in a sanctuary, visible but untouchable until we earn their attention. If you found Brian Cox's perspective as fascinating as we did, don't forget to hit that like button and subscribe for more thought-provoking content. Got your own theory on the Fermi paradox? Drop it in the comments. We'd love to hear what you think. Until next time, stay curious.